Yeah. Hi, everybody. Thank you for the kind introduction. I have nothing to declare. So one of the most interesting scale at which we can look into the human brain non-invasively using the strength of the ultra-high-field magnetic resonance imaging is the mesoscopic scale. And I hope that many of you here agree with me. At this scale, at this scale, we can start looking into the interesting interaction across cortical area at the level of cortical layers and cortical columns. However, cortical layers and columns appear themselves as a spatial feature inside the neocortex. Therefore, it's really relevant to combine this with a spatial feature of the vasculature, which is feeding this feature to appear functionally. So in this study, we are trying to address the following question. How does the vascular architecture and the spatial distribution influence the spatial specificity of layer fMRI Ball signal? In order to do that, we are building on the Frisco approach, which was recently developed and presented last year at ISMRM by Renzo Huber, which allow you to push the spatio-temporal resolution in almost uncharted territory. So check out the latest development if you're curious. For the vascular imaging, we are also based ourselves on the mesovein protocols, which I refer later in this presentation with this naming, which was also recently published in early this year by one of our collaborators, Farouk Urban, which allows you to provide the whole brain mesovein mapping at 0.35 millimeter isotropic under 7 minutes. And both approaches have been developed on clinical 7 Tesla MRI scanner. So in our study, we are bringing together these two very exciting approaches. So we collected data on a clinical 7T scanner for 6 healthy individuals over multiple scanning sessions. In one session, we fully focus on vascular imaging, so getting T2 star-weighted images at 0.35 millimeter isotropic for the whole brain. And in the remaining 2 sessions, we employ 2 different Frisco protocols that are still both weighted. So one target the visual cortex in a very tiny slab, and we obtain a 0.39 millimeter isotropic resolution. And the other one, the complementary, I would say, we collect the whole brain at 0.8 millimeter isotropic resolution. And in both cases, the participant, while lying in the scanner, was exposed to a flickering checkerboard. So a very simple visual task, 30 seconds on, 30 seconds on. At the same time, it was also performing finger tapping. So both a Frisco protocol met our quality control criteria quite nicely, as you might see from the TSNR reaching double digit in both cases, or from the temporal modulation, which is very clear even at single voxel level after few averages, of course. I also want to point out that when we compute just the mean EPI at 0.39, we can start even seeing with the naked eye some mesoscopic structural features, such as the layer 4, for instance, here, or some intracortical vein. Okay, when we translate this into activation map and we put side by side the 2 resolutions for the same subject, we can immediately see that there is a lot of variability, spatial variability of this activation map at 0.39. Even if you zoom in a tiny part of the brain, you might appreciate that there are some profile which we can approximate to a middle layer bump. Some others that look like columns, but there is way more to explore. And compare now this with what you can see at 0.8, which everything looks a little bit more blobby. Okay, this was just one subject, and we have consistent and reliable activation map with the same feature in all our subjects. Moving on to the laminar profile, we compute normalized cortical depth measure using the equivolume principle, and in our small coverage defined as 0.39, we also compute geometrical cortical columns, which will help us to disentangle some of the variance in our data. So first of all, we pulled out all the laminar profile from these individual columns, and we compare the average profile across the 2 resolutions. And here I'm plotting you the standard deviation across columns. So you might see immediately that the shapes look a little bit similar, similar, but we cannot deny the huge variance which is across the columns. So one way to tackle this problem is to look into each single profile coming from these columns side by side at the 2 resolution. So here, as a comparison and as a complementary information, I'm also showing the anatomical laminar profile for all columns. Columns here, cortical depth on the x-axis, deep to superficial layers. So what we see is that there are some profiles that they look very similar to each other when we compare the 2 resolutions. So in white, I'm showing you the 0.39, and in cyan, the 0.8. However, there are so many more profiles that they look very different, as expected due to the increase in resolution. So this is a specific case that I would like to point it out, which is not due to a single column, but it's a pattern repeated over multiple columns, which are all clustered here. So while at 0.8, we just see this increase towards surface pretty strongly, at 0.39, we are observing consistently this middle layer peak in multiple columns, even though there is a progressive linear superimposition effect with a linear increase from the left to the right side that I'm pointing here. So this is let us wonder how much the pial surface actually is affecting the draining vein in this new regime compared to the intracortical draining. For this reason, we look into the pial surface, we open up the calcarine sulcus, we take out, virtually of course, the inferior bung of the calcarine sulcus, and then I'm rendering here what remain if we compute the inverse of the tissue star-weighted images. So in bright, you see that the vasculature is all highlight. And I overlay on top of this the activity that we obtain at 0.39 and 0.8. And I hope you can appreciate how tight the activity is following this venulus inside the cortex on the pial surface compared to 0.8, where everything looks a little bit more blurry. Okay, I also would like to point attention to another type of profile, which I found very interesting. This is the opposite of before. So now we have a strong decrease towards surface. And there are many profiles like this also across all subjects. So where is it coming from? Well, let's look a little bit in detail on our activity. So I'm superimposing our mesovein images with the tiny slab at 0.39. And the blue one indicates the negative activity. Look, and I'm going through slices. See how nice we can actually see that there is a negative activity going on into the calcarine sulcus. Now let's compare it with 0.8. Yes, we do observe again that there is a negative activity going on in the exact same location. However, everything looks a little bit more blurry. But the point here is to see that this negative activity doesn't only occur in this part of the brain, but also way lower in the inferior part of the cortex, here. So we had an intuition that this activity, negative activity, might follow the spatial pattern of some vasculature, and specifically we thought about an artery. Therefore, I used the T2 star-weighted data to highlight the vasculature and reconstruct part of the arterial tree, starting from the brainstem artery until to the visual cortex. And next to it now, I'm reconstructing the negative activity at the 2 resolution. And I hope you can see how closely it follows the anatomical arterial tree. And with that, I would like to conclude and highlight that at 0.39, we have a lot of variability, and we need to keep learning about our layer fMRI result and improve the interpretability. And I hope that the vasculature will help us in this task. With that, I would like to thank you and take some questions.